for you. Okay, cool. So yeah, so as we said, we will go through the concept of self-attention and multi-head attention. So have you guys actually like get exposed to these topics or?
No, don't need to.
I think probably you have.
I only know so much because, like, to me, self-attention, it's basically understanding the context, right? When you have a sequence,
Mhm.
like the idea is, not only like you look for the occurrence of certain words, but then you try to, like with a sentence, you try to figure out, okay, what is the how is a particular word relate to another word. Like some of the example I've seen is I love you is different from you love me. No, John love Mary is different from Mary love John. Although the both sentences have the same words. If you try to like use machine learning trying to figure out what is the meaning of sentence just by checking out the occurrence of the word, it's not going to do it. You need to understand context. You need to understand John. It's like the word love is related to the subject, and who is the object. That's the like that's that's the idea.
Yeah, I think that explains pretty much it and very well. Yeah, so like as you said, it's basically to find out about the associations between the items in the sequence, right? So it's more like when you okay, so and then for a self-attention mechanism, it's actually done in both encoder part as well as the decoder part. So so yeah, so it provides like the when you're trying to find association like for one of the token in the sequence is kind of like scanning through the entire sequence and then zoom in the most relevant tokens in corresponding to each other, right? So I guess for that, then I would say it's so it would be like the attention self-attention mechanism is good to find out about like the multicollinearity, or it could also help for feature selection, right? It's like it kind of like provides these functionalities, and so like it actually serves different purpose in encoder attention and decoder attention differently. So for encoder attention, as we know, encoders mostly serve the purpose of embedding, like finding, like the embeddings of the tokens in the NLP domain. So therefore, so the encoders, then you're kind of like when you're inputting a sequence of tokens, then it's actually projecting each of the token into a vector space, right? So then the then the self attention in this part of the transformer model then is to find out that in order to generate the embedding for each of the token, how are you actually blending the vectors of other tokens into generate the token that you want to project, right, to the vector space. So this is the purpose of self-attention mechanism in encoder. But for the self-attention mechanism in decoder, then it's like when because actually decoders for decoders it really depends on what is the task that you're doing. So sometimes so therefore decoder attention is really task specific. So decoder sometimes if you're doing say a machine translation, then then the decoder when you're doing is actually say when you're producing or outputting the next let's say I am a student, right, in English, and then you want to translate it to French, like je suis étudiant. And then when you're like say decoding up, like you want to translate the student word, like it's up to the step that you're producing the étudiant token, then the self-attention then helps the model to know that, you know, at this step, which token in the input sequence that you should mostly focus on when you're decoding this step. So yeah, so that's that. But let's say that if you're not really doing machine translation, but you're really doing uh, like a classification model. Let's say that when you are trying to say classify like let me think about like okay, so let's say that you're trying to classify like a dog picture versus like a human's picture. Then your output, your decoder would output, let's say zeros or ones, right? In this case, whether it's a human or not or an animal. Then in the input sequence, then you would have the features of that picture of that either a human or animal, right? Then when you're decoding, when you're outputting that classification category, then you are like, then that self-attention in the decoder, it will mostly then focus on the features that will best identify that it's a human, right? So therefore, it's actually doing the predictive powers feature selection, right? It's basically choosing, assigning the weights to the features that actually help you to identify the best for a human being. So therefore, the weights, if you did traditional machine learning before, then you know those feature selection like algorithms, either like say a random forest or a tree decision tree can do. So this type of self-attention weights, these weights are like kind of like the same serving that purpose of the decision tree. I guess either it's a Gini index or say those weights. So it's kind of like doing similar purpose, right? So it's basically identical, like assigning the weights to the features that best predicts what you want to output. So this is the self-attention mechanism in decoder. So this is a difference between this is a difference of self-attention between encoder versus decoder. So self-attention encoder is to best to help you find a blend the weights, like to blend the input tokens to produce embedding vector for your token. But then decoder is actually self-attention is to help you identify the features that best predicts the output of your current time step.
So I just want to make that. That's very
Yeah.
interesting. So on the encoder side, the self-attention is, can I say that it's kind of eliminating or reducing the noise and let you focusing on the feature that you'd be mostly interested in?
Actually, both are
Okay.
are reducing the noise, right? So it's all reducing the noises
Yeah.
and then zooming in on the most relevant and important stuff, but it's just the purpose of them are different. So in the decoder part is to reducing the noises to help you to find the best predictive features for your output.
Yep, yep.
But for encoder is to reduce the noises and then only find the relevant tokens to project your token into a vector space
see.
to find a representation, or in say, because we know that attention mechanism, it's not only exists in transformer model, it also, you can like apply attention mechanism in almost any model. Let's say that in the pre-transformer model, if it's the recurrent neural network or sequence to sequence model, you can also apply attention mechanism. But in this case, it will be, let's say that if it's an RNN, then each of the RNN node, right? It produces a hidden state for that input, and then if you will work with a sequence to sequence model, so it has encoder decoder for translation, machine translation, and then for your like encoder part of sequence, right? So what you do is you go through all the nodes of the RNN, and then you output the final hidden state, right, of your encoder. And then that final hidden state is supposed to contain the knowledge of your entire system up to now. And then you input this final state of the sequence into the decoder and produce. But that's why RNN would suffer the vanishing gradient descent problem, that if your input token or your input sequencer is too long, then it might actually forget something that happens at the very beginning and only probably the recent memory. But if you apply self-attention to this recurrent neural network, then actually your decoder would use every hidden state of your input token. So it would actually not just using the final hidden state of the final node, but it would actually scan, right, your entire input sequence and find the most relevant tokens hidden state, and then do like a weighted average, weighted sum to generate the token of that input token. So therefore, attention mechanism solves the problem of losing memories of long sequence. And it also helps to actually, yeah, like you said, reducing noises. Yeah, so that's what the self-attention mechanism work in both encoder and decoder. And then another one. Okay, so in terms of the actual calculation or like technicalities, there's like it's nothing more complicated than like a weighted sum algorithm. So just yeah, like so it's just like finding it's a basically linear combination of your input tokens, and then through training find out uh like the weights should be optimized uh assigned to each of the linear combination weights, right? So that's the essence of the calculation for attention mechanism. And then so then for that, then we know that transformer model not only has one set of attention mechanism in either encoder or decoder, but it actually, for transformer model, it actually has multi set of these attention mechanism, specifically 8 of them, right, in each of the encoder and decoder. So So then people may ask then why why you would need so many set of copies of attention mechanism. For me to understand it, it would help to use the analogy of when you are doing a stochastic gradient descent, right? Because like all these machine learning models, all of them are not what is the word called? I forgot about, I don't know, like after COVID, I think I have so much brain fog. So there's one called computational solution. Oh, okay, yeah. So in this thing, there's something called I just thought, but there's something I forgot. There's computation. Oh, there's analytical solution and there's computational solution. So analytical solution is something that you like, especially in the optimization theory, right? Like analytical solution is some solution that you can actually solve, giving the answer by precise, like deterministic way, right? But then the computational solution is something you use like either iterative algorithm, yeah, mostly iterative algorithm to for optimization to get the solution. So we know that all of the machine learning solutions are almost like computational solutions. So therefore it's through iterative optimization, right? Like you run for deep learning models that you have to, that's why you have to run through different epochs, right? Like of the entire training data set. So therefore, first like for stochastic gradient descent, if you wanna recap, how does it achieve it is because we know that for in order to get the optimized parameters, right? So mostly people give examples when they're using stochastic gradient descent. It's the least squares estimators, right? So for least squares estimators, you can either achieve it in the mathematical way, that will be the analytical solution. So you will actually find the exact, like a formula to calculate it. But in computer science, in computational solution, you actually start like basically if you remember that like you start from like at the tip of the mountain, right? And then let's say that you want to find the minimal point of this like manifolds or this like mountain, then in for computational solution that you actually start from like a random place on the mountain, right? And then through iterative optimization at every step, then you stop, right, at some place, and then you claim that, okay, I found the valley or I found the minimal point of my whatever the mountain, right? But then here comes the question that then it really depends on where you will start on your mountain, right? Then where you will end up to be the minimal point, right? And then so therefore it's the same thing for multi-head attention, right? Because if you remember, okay, so I guess for the detailed technicalities, I will leave some room for us when we are, doing the roundtable presentation. But like anyways, if there's a matrix, right? Matrix to because almost all machine learning problems is an optimization algorithm. Then optimization algorithm, then you have to start with some random vectors, random initialization of either a matrix or a vector. So the same thing for to find our optimize the weights, right? To assign for our attention weights, we gotta start with a random matrix. Then it's like the stochastic gradient descent, right? So like then where like it's random matrix initialization, that what if your random matrix initialization doesn't work as well, right? Because it's all by luck, right? Like on the mountain, it depends where you start randomly, that kind of determines where you would end up, right, at the minimum point. So therefore you would give the model more chances for these type of random matrix initialization, like on the mountain, right? So therefore, in transformer model, it gives the model 8 chances, right? To hopefully actually find the best, chances to actually achieve that minimum point. And then so that's the eight sets of the path to find the optimal weights. And then ultimately it would also blend them, like doing another weighted sum linear combination of these 8 chances of trying. And then so the good things about this type of weighted sum is that like just like stochastic gradient descent, right? If you actually start at the random point, which is not good enough, then you might actually end up on a local minimum, right? Instead of the global minimum, right? But if you do it 8 times, then that increased. So every time of these 8 times, then that increases your chances of actually finding the better minimum point, and then you kind of like average them out. Then it's better than one bet. So you give like 8 bets.
Can I try to
Yeah.
just want to make sure like you're all on the same page, right? Basically, I think what Harriet is saying is like we're looking all these AI solution. You can treat it as a numerical problem. Like I don't know if you've seen this like 3D like contour that like
Yeah, I see
that's the contour of the solution. So what happens is we're looking at something called global solution, global maximum or minimum versus a local maximum or minimum. The global one is your real solution. That's the best solution. No, nothing it's better than this. The problem is it depends on where you start, right? If you start somewhere close to a local minimum, you keep searching. Oh, that's a minimum. That to me it's a solution. However, what you might not know is if you keep going, even though you're moving away from the solution, you're hitting a mountain. Once you pass that mountain, there might be
You have
another
better
solution.
views.
Yeah, that might be another solution which is better than this. So that's why she's saying that with the multi-head attention, like basically the transformer has to start somewhere. So it's a random thing, right? It will randomize some matrix and start calculating. The problem is if you pick one set of value, you're starting somewhere. That might run into the situation I was just talking about, it hitting a local solution. You thought, oh, I'm there.
Yeah.
That if you pick from different points, then there might be a better chance you will actually see a better solution. You might see, okay, with 8 different initial points, I would get 8 different answers, and I'll just average it out. Hopefully, that will give me that will increase my chance of hitting a better solution rather than, as she said, like putting all my bets in one place.
Yeah, in one basket. Yeah.
Now my question, I have a question is like the magic number 8 is always 8 or it depends on the
In transformer model, it's 8.
it transform model.
Yeah,
It's
so
a random number. It's empirical. People just pick something.
yeah.
Okay.
So I guess it would be another hyperparameter that you would potentially be able to tune. But in transformer model, they just set it 8. Yeah. Maybe there's a reason why they pick A. Maybe through, like you said, it's empirical, through like different experimentation from the transformer inventors. yeah, so the good, exactly as William said, then so it's basically the eighth one is to be able to let you see like different aspects of the mountain, to start from different places of the mountain, right? So you have better views, like holistic views about the mountain, like the contour itself. So in terms of specifically, if we are putting it into context of NLP or the perspective of NLP, then um, each set of these multi-head attention, let's say that if we are talking about attention mechanism in encoder, then each set of these attention mechanism is actually ultimately projecting your word, right? Word token into the vector space, like vectors of your representation, right? Like you're trying to represent a word token with a vector, a numeric vector. So with each of the, but let's say that like a human language, let's say that a sentence, uh, to actually embed, project a word token into the vector space, human language actually has many different aspects, right? So we call that semantic, right? Semantic representation of human words. So like say in attention head one, then you are maybe projecting your human language in the representation space, vector space of say simply just the meanings. And then when you start with another random matrix head, then you're projecting human language in terms of its grammar or lexical grammar representation. And then a third head attention layer then is projecting human language in terms of say sarcasm, like in the perspective of sarcasm, and like the fourth attention head may be projecting your human language in terms of say like ethnicities, right? So you're basically constructing or projecting the human language tokens into these different representation subspace of the human language, because human language is multifaceted, right? Like you can actually interpret human language in different perspectives. So therefore, with these different different head attention head, you're actually finding a different perspective of interpreting or aspects to project, to interpret your words. So therefore, it would first then enhance the, and then ultimately after you find all these eight representation subspaces, ultimately you would also blend them together to summarize your human language in a summarized way through just different angles, right? To look at your human language. So therefore, the embeddings that is obtained through multi-head attention is more holistic view of your human language and is more multifaceted and also more complete, right? More complete representation of your, so therefore it actually would obtain a more precise like interpretation of your human language. So therefore that's, and then also another one is through maybe all these eight heads of attention, so maybe one of them would let the language to focus on closer, more adjacent when you're in JSON tokens of when you're embedding that token. And then maybe some another hat would actually focusing on specializing longer or remote tokens from your current token, right? So therefore, not only it focus on different aspects of representing your data, but it also better chances for if your input sequence is really long, right? So then it also enhance the model's ability to embed really long range of sequence as well, right? And then the third good point is that it would also help to reduce the overfit possibilities for your model, is because one head actually specialize in representing your data in one specific way, but you have 8 of them, right? So therefore, and then you averaging out all these 8 ways of representing your data. So therefore, your representation is a more smooth a way of represent your data. Wouldn't be like like just like a focus or specialize in one, not like extreme or sided or biased way of representing your data. So it has these 3 good points that I summarize in here for a multi-head attention. And then another good thing is that this multi-head attention, like it's actually good for parallel computation, because you can process these 8 heads at the same time, right? So one of them is not really interfering with another, so therefore this multi-head wouldn't make your computation taking more time, right? So therefore it's efficient, right? Yeah.
I will remiss. So this is multi-head attention is only using for encoding or using for
Both.
encoding, or both are okay.
Yeah. So because you know that for both encoder, decoder, we have attention mechanism, and then not only we have multiple copies of them in each of the encoder and decoder.
So then the X is like a total from encoding to decoding is exactly, or individual one have exactly.
No, what she meant is the multi-head thing, it's basically having 8 different copies. It's doing similar things, but
Okay.
looking at different angles. It's like, okay, you have a math problem. Instead of just you having one guy solving it, you ask 8 different guys, but they look at it a little bit differently. They start from a different starting point.
From endpoint to endpoint, from encoding to decoding.
Yeah.
That's
Yes.
a big process for it. Okay.
Yes.
Okay.
Yeah, encoder you have 8 copies of them, and decoder you have 8 copies.
Okay.
Yeah.
Okay.
Okay, so that's, I guess that kind of gives a kind of like a overview of self-attention and multi-head attention. So now we just categorized them into 4 categories of this topic. So the first 2, one is self-attention, intuition, and purpose. Second one is self-attention, algorithm. So it's the detailed calculation, how you implement self-attention, right? And then the 3 and 4 is about multi-head intuition and multi-head calculation. So each of us would pick one of it to do research for like 30 minutes, and then we would do a roundtable discussion. Yeah, for each of them. And then and so then we can actually get a deeper understanding by active learning from ourselves. So okay, we can start from Caleb. You can pick any of the 4 to talk about.
I will try the first self-attention, intuition, and purpose.
Sure, yeah. And then we can go to Willie.
What do we mean here for algorithmic attention?
So the detailed
how it's being implemented.
how it's being calculated, like the actual algorithm, how it's carried out. Say weighted sum, like, and then how do you like assign the matrix, and then how do you do the sum?
I think I've seen the formula before, but I never understand what it
Yeah,
is.
so we will give 30 minutes
Okay,
for each of
okay, I
these.
can try the second one.
Second one, okay, sure. And then you wanna pick from 3 or 4.
To number 3.
Yeah, sure. Okay, so then I'll do number 4. So we will then give each other 30 minutes to prepare for that, and then we will start the roundtable talks. Okay, so that's it.